Okay, looks like I've got your homework 5s. 2 weeks is too much time for a homework assignment, right? It just doesn't feel good when you've got that much time. It's better when it's just like back to back and the stress levels are up and your efficiency is high because you're in panic mode, fight or flight, so you're working real efficiently. So I'm glad we're back. Yeah, right. I'm going to die. I got to get this one done. Yeah.
It's like a ticking clock on it.
Exactly. All right. So homework 6, as I announced in email last week, is due on Thursday. And I know a couple of you have already taken a crack at some of those problems. We'll go over some examples during class today that will round out your abilities for that assignment. If you compare this to the initial class schedule, you'll notice that there's 2 problems that was on the original class schedule that you don't need to do now. So definitely refer to this revised list. And then we're going to have the exam in class on Thursday. Only 3 questions, like I said in the email. Those are all going to be problem-solving questions. And you can prepare an equation sheet, but the equation sheet shouldn't have solved examples on it. It's okay to have formulas. It's okay for you to have maybe a brief outline of a procedure. Any questions about the exam? The coverage is from the beginning of the semester up until today's class. So, Brandon? I haven't written it yet, so I can't really say what it's going to be more of and what it's going to be less of. Yeah. But we only have 60 minutes, so I wouldn't expect that I'll have the flexibility to give you problems that are too lengthy. Unfortunately, because I really love giving you lengthy stuff. Yeah?
If there are computer questions, will we use previous like Excel algorithm?
Definitely not. No. You'd need to start with a blank spreadsheet. And so with that in mind, your equation sheet, you can put column headings on that equation sheet, like remind yourself it's R times Q times absolute value of Q, NRQ times absolute value of Q, all that. You can put the column headings. Yeah. Including today's lecture, yeah. Yeah, all 3 questions will be from today's lecture. No, just kidding. All right. Other questions before we move on? That was a joke. Okay. All right. So we're talking about pumps today, and as I mentioned in the email, we're going to have to cram 2 different lectures into today, and so I've eliminated and scaled back a few of the things that we'd spend a little bit more time on. Here's just a couple of hints before we get into it on the homework assignment that you've got to do on Thursday. For those of you who aren't as acquainted with the SI units, a metric ton is 1,000 kilograms. And so in that problem 9.5, it doesn't say a metric ton. I think it just says a ton. Don't use 2,000 pounds. Use 1,000 kilograms for that problem. And also on that one, they refer to something as the coefficient of friction. Basically what they're doing is they're defining the F value, and so you don't need to iterate to calculate that. You're not going to have to use the Jane equation. You can just straight out use that coefficient of friction as F in the Darcy-Weisbach equation. And then problem 9.6 is a mixed units problem where they're both giving you some stuff in SI and you're going to have to work in traditional units. And so to convert the kilowatts that are provided into horsepower, that conversion is in the front of your book. And there's 1 kilowatt equals 1.34 horsepower. All right, so let's talk about pumps. It's so bright with the sun, you can hardly see the screen. This is something that's called a screw pump. It's a picture of a screw pump, and it's a positive displacement pump, which means each revolution of this pump, it looks like a screw, which is where it gets its name from. Every time it rotates, there's water, and this is tilted. We're looking at a front-on view of it, but if we were looking at it from the side, what we'd see is that it's tilted like this. And so here's the stream, and the screw pump's going down into the stream, and it has a screw shape, and every time it turns, there's some water here that's being lifted. So with each revolution, a certain fixed volume of water is being lifted to the top, and then when it reaches the top, it just sort of dumps out and then flows onward. And so this positive displacement pump adds energy in the form of elevation. And you remember from the energy equation, there's three places that the energy can be. It can be pressure, elevation, or velocity. So you'll remember that when we graph energy with the EGL, the three terms of the EGL are pressure head, elevation head, and velocity head. And so this positive displacement pump is lifting the water. And so it adds to the Z value of that water directly. Most pumps don't operate this way. Positive displacement pumps are pretty rare. You'll notice this looks like a rustic setting here. We've got like a cobblestone creek and a wooden fence. So this is obviously some big industrial area. It's kind of a historical site. So I think these little animations are interesting. These are examples of positive displacement pumps that are a little bit more common, although still these are specialty applications in each case. The one that I've used the most is a peristaltic pump. And this is used in environmental engineering applications when you want to deliver a constant flow rate of a liquid, and it's a very low flow rate. What's useful about a peristaltic pump is you can put in a different diameter tube, and so what this rotating wheel is doing is it's pressing the tube, and you can see that it's causing water to be sort of pulsed out of the pump. And if it's a very small diameter tube, each rotation isn't going to deliver that much flow. And so I used a peristaltic pump to deliver on the order of like less than a liter over a week. When you want to transfer a really, really slow flow rate of liquid, a peristaltic pump is very useful. Another one that I think is especially interesting is a rope pump. And these are used in a lot of really rural settings where it's maybe a community well. And the nice thing about a rope pump is that the parts are really easy to fix. It's basically just a series of plugs attached to a rope, and each revolution of this hand wheel at the top is causing the plugs to go through a pipe, and it's the fit is going to be very tight between the plug and the surrounding casing. And so you can see that as the plug goes upward, it's forcing the water out of the pump as well. So the rest of these work in much the same way, that a rotation is delivering a certain volume of water. These are not the way that most pumps work in municipal water delivery. By contrast, most commonly we're using radial flow pumps or centrifugal pumps. And these work by accelerating water and adding pressure instead of adding elevation. And so the way that it works is you have an impeller inside there that's spinning around very quickly, and it has different shaped blades depending on the configuration of the pump. Some pumps are designed to operate with a very high RPM, some slower RPMs, and the blade shape and thickness varies accordingly. But in each case, what's common to it is that the water enters in one direction on the suction side, and then it exits the pump in a different direction. So it's coming in and it's changing directions like a 90-degree angle. One thing to point out is that sometimes people say pump when they mean pump and motor together. And in your homework problems that you're going to be working for Thursday, sometimes the pump and motor are considered individually, like the electrical efficiency of the motor is specified, and then the efficiency of the pump at converting electrical input energy into additional fluid head is separate. And so those are two separate things. So don't confuse pump with pump plus motor. And we'll work an example problem where both of those are considered individually. Okay, related is an axial flow pump. And here you can see the difference with an axial flow pump is that the motor is going to be some distance away from the impeller. And so the energy is transferred through a shaft. And usually in the case of an axial flow pump, what would be common here is to have the motor at the surface. Let's say you're pumping water from an aquifer, which is deep underground. This allows you to have the motor at the surface, and then the shaft goes down deep underground until it gets to the water level, and then you can have the impeller beneath the water line. And that makes it easier to prime the pump when it's just first getting started than if the impeller is up at ground surface. It's really hard for a pump to suck air up through the casing till it finally fills with water. And so axial flow pumps, the advantage here is it just allows you to separate the location of the motor and the impeller. All right, so now let's look at one of these in the side view and talk about what's happening. What is the pressure of the water right here at the surface? It's 0, right. And so, remember that if it's in contact with the atmosphere, the symbology we use to convey that is the little triangle and then the ripples underneath the triangle. That means that it's touching the air. And so if we say let atmospheric pressure equal 0, so we're talking gauge pressure here, the pressure is 0, and then as we go down through the fluid, the pressure is increasing. So the water is going to enter this suction side pipe, and the water will first go through a very coarse strainer, which is just meant to keep leaves and branches and any sort of debris that would damage the pump. The strainer is doing the job of keeping that out. So the pressure is positive as it first enters this pipe. But the pressure is going to be decreasing in the direction of flow. And that's why the water is going from one place to another, is it's moving from high pressure towards low pressure. That's why the water is moving. And so what we know is that we have some positive pressure that corresponds to our depth. And then as we move upward, about here, where the water level is on the outside of the pipe, we're at 0 pressure. But then 0 gauge. So we're still moving through the pump. The pressure is now negative gauge. It's not negative absolute pressure because there's no such thing. The lowest you can go in absolute terms, of course, is 0, meaning a vacuum. But here, inside of this suction side, we're moving closer and closer to 0 pressure, and what we hope is that the pump occurs before we get below the vapor pressure of the liquid, because that can cause cavitation. We'll get into cavitation a little later. But the pump itself is just adding a huge increase in pressure. And you'll remember that when we were doing drawings of energy grade lines last semester, and we had a tank pumping water to an elevated tank, the way that we depicted the energy grade line is we said it's going down, and then suddenly there's a huge jump, and then it's going down again. And so that huge vertical line, what we were drawing there is a sudden increase in energy. And going back to the EGL equation, it's not that we are physically adding elevation to the water through this pump, because the physical elevation of the water as it moves through the pump doesn't change. On the left of the pump, it's still at the same Z value as the right of the pump. And so we didn't physically lift the water, so it's not an increase in Z, and it's not an increase in the velocity, because assuming we have the same diameter pipe, in and out, velocity in and velocity out have to be equal because of continuity equation. Remember that Q in equals Q out. And so A in, V in equals A out, V out. And so if the cross-sectional areas are the same because of the same pipe diameter, then that means velocity in and velocity out are equal. So this pump isn't adding energy as elevation. It's not adding it as an increase in velocity. It's adding it as an increase in pressure. And so on the downstream end of the pump, the pressure is very high. And then as the water flows through the pipe, the pressure is gradually decreasing because of pipe friction. So any questions so far about what this pump is doing or how it works? All right. One other thing to point out, you'll notice that they have a check valve here. The purpose of that check valve is to make it easier to start the pump after it's been off. It's not easy to start a pump if it's full of air. You can hope, and some pumps are pretty good about getting primed without being filled with water. But if it's just full of air and you turn it on, those impellers are spinning around inside of the pump, but they're designed to accelerate liquids, not to accelerate a gas. And so some pumps aren't very effective at creating the vacuum required to suck the water up into the suction side pipe and to fill the pump. And so it's just easier to have a check valve so that the water can only go towards the right, or the water can only go out of the pump and not back towards the water. And if this pump isn't able to self-prime, then what you have to do is you have to have a valve down here and close it, and then take a hose and try and fill up the suction side and fill up the pump, and then you can turn it on. So those kinds of pumps are a little bit hard to deal with. In the case of this axial flow pump, you'll notice that the advantage here is that the impellers, you can make it below the water line, and so priming this pump isn't going to be an issue because the water is already in contact with the vanes. And so as soon as you turn it on, that water is going to start flowing through the pipe. It doesn't need to create a suction to begin with.
Yeah, how is the pump actually adding the pressure?
It's adding the pressure because it's accelerating the water inside of there. And you'll remember that when we were talking about convective acceleration, that increases in acceleration increase the pressure. And so it's basically having to do with the shape of the blade, and there's going to be more pressure on the outside edge of the blade than on the inside of the blade. And so it's similar to how a wing creates lift. And as that impeller is spinning around, there's more pressure on one side of the impeller than on the other. That's a good question. All right, so you're going to need to know about efficiency in the homework, and ideally, the power required to move water can be calculated by this equation. In SI units, it's the flow rate in cubic meters per second, the unit weight in newtons per cubic meter, and then the pump head in meters. And so if you multiply those three terms together, what you'll get is the power in watts. And just a special note, maybe put this in the margins, that it doesn't give you kilowatts, it gives you watts. And so a lot of times these problems the power is described in kilowatts because that's how power is sold in terms of kilowatt hours. And so keep in mind the conversion that there's 1,000 watts in a kilowatt. Okay? Now in the case of BG units, the flow rate would be cubic feet per second. The unit weight is pounds per cubic foot. The pump head is in units of length, so it's feet. And then this 550 converts those three terms into horsepower. So this is ideally. This is how much power is required if the pump and the motor were 100% efficient. But they never will be. Both of those are going to have some losses associated with them. In the case of the motor, when you put electricity into a motor, it's going to be heating up, and that's where the majority of the losses are. But there's also vibrations and sound, and so some of the energy is lost due to that as well. In the case of the pump also heats up. You're going to be applying energy to the shaft of the pump, and as it spins inside of the pump, there's friction, and so some energy loss is going to mean that your overall efficiency is just the product of the motor efficiency and the pump efficiency. So compare the ideal pump equation to what I'm calling here the real pump equation. You know, in real world application, you'll have some efficiency that's maybe, if you're lucky, around 60% when you consider both the pump and the motor. And so ideally, maybe you needed 1,000 watts to move the water at some flow rate and with some pump head. But you'll notice since you're dividing by a fraction that's less than 1, your actual power is going to be larger. So if it was 1,000 watts that were needed ideally, and you have 60% efficiency, you can see that I should have picked something I knew how to do the math on. What's 1,000 divided by 0.6? Like 1,400? No, more like 1,600? Mary's going to help me out. 1,666. All right, watts. So you can see that you're going to need to give more power to the system if you need to have 1,000 watts added to the water. So this P here is how much electricity goes into the motor, and this P is how much energy actually gets into the water. Okay? And the rest of it is losses, mostly to heat. Any questions about efficiency? Now, efficiency varies not only from pump to pump, but even if you have one given pump, it may be have different efficiencies depending on what flow rate you're operating it at, or what speed the motor is spinning, or how high it's having to lift the water. And so one of the big jobs for engineers that are selecting pumps is to go through these page after page of efficiency diagrams and try and pick out the pump that has the highest efficiency at the conditions you expect it's going to work at. And that can be really a big job. And so there are some manufacturers who hire engineers as salespeople, and all they do is help people pick the right pump for a different application. We'll take a look at one of these efficiency figures in a minute. All right, so a pump, when you get one from a manufacturer, they'll have a table that describes how it operates, or it may be depicted graphically like this. And the way this diagram works is that it can lift the water only a certain amount of elevation. Here is an equation, just, it's not always 24.4 minus 7.65. This is just an illustration of the form of the equation. This 24.4 means that's the intercept on the y-axis. And so at most, this particular pump can lift water 24.4 meters. But when it's lifting water that high, it does so with a flow rate of 0. And so if you want to actually have some appreciable amount of water moving through the pump, then it can't lift water this high. And so let's say you needed 100 liters per second, and that would be here. You'd go over here, and you'd find out how much pump head this system is having added to it by the pump. And then you can take the head, and that'll tell you how much pressure the pump is adding, because the pump head multiplied by the unit weight is the increase in pressure. And so H sub P multiplied by the unit weight will give you the increase in pressure that's added by the pump. And so what is a pump working against? Well, the pump is overcoming friction losses in a system. And in this reservoir-to-reservoir transfer that I drew, part of the work that the pump is doing is dealing with the fact that as water flows through these pipes, the material is pushing against the movement of the flow. There's a roughness of that material. The water is flowing through the pipe. So there's a shear stress applied by the pipe material to the liquid opposite the direction of liquid movement. So the water is moving to the right. The pipe is pushing on the water. The pump is working to overcome that. It's also working the elevation difference. And then it's also pressurizing the liquid. Sometimes you're wanting to lift it primarily. Sometimes you have a pump in place just to increase the pressure. Like if people are complaining about the water pressure being too low at their house, adding a pump isn't going to change how high the water is, but it's going to increase the pressure in the lines. Now, the absolute rule is that as the head increases, the flow rate decreases. Or we could say vice versa. As the flow rate increases for a pump, it's not able to add as much head. So here's that declining rate curve that we'll see in your homework, and here in a minute when we look at an actual pump diagram that's provided by a manufacturer. So we call this the pump performance curve. And later on, as we go through an example, I'm going to tell you to set this pump curve equal to a system curve. And that can be you can solve it graphically or you can solve it numerically. And to solve it numerically, you'll have to have it in this form, where HP is on the left side. You've got some intercept, where the intercept, the 24.4, that's just where the curve went up here in the y-axis. And then negative some C value, a coefficient that allows you to have the curve that's expected. We'll talk about that. Okay, so this is the pump curve. Here is how we create a system curve. In the image here, we can see a system where water is being lifted. The water is flowing from a lower tank to an upper tank. You'll notice that it's got a submerged entrance here, so we're going to have some K values. Remember, K values are associated with local losses. And so a local loss is an energy loss just at a single point that's maybe due to a fitting or due to a change in direction or an entrance or an exit loss. And so here in the system we've got an entrance loss where energy is being lost just because of turbulence here. Here's going to be a local loss, another one there, here at this bend, and then a discharge loss. So those are the local losses, but then there's also frictional losses that the pump has to overcome, and then finally a delta Z. And so we can represent the amount of energy that's required to overcome this system as a function of the flow rate. And that's just what I've drawn here is a typical shape of what we're going to call the system curve. And the way that you create that shape is by writing the energy equation in terms of a flow rate. So I've rearranged our typical energy equation where we usually say Z1 plus P1 divided by gamma plus V1 squared divided by 2G plus HP is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus HL. And by head losses, what I mean is both the frictional losses and the local losses. And then if we had a turbine, then that would be over here on this side as well, H sub T for a turbine. Well, here there's no turbine, so I'm going to erase that term. And if we rearrange the energy equation just in terms of H sub P, then here's the system curve that we're going to be writing. If we're writing it from location 1 being the origin reservoir and location 2 being the destination reservoir, since both of those are open to the atmosphere, both P1 and P2 are 0. So that's why there's no pressure terms in this equation. It's just the delta Z, how high the water is being lifted. And then I've written the head losses in terms of Q. And remember that when we use the Darcy-Weisbach equation, we usually say FL V squared divided by D2G. But it's easier for us to do calculations sometimes if we represent that. Instead of writing it in terms of velocity, we write it in terms of flow rate. FLQ squared divided by D2G A squared. And that's what this is. So here's the friction loss term. Here's the local loss term. That's due to those bends and the entrance and the exit losses. And it all depends on the flow rate. So this is telling us that at 0 flow rate, how much energy do we have to add to get the water from the lower reservoir to the upper reservoir? If we have a very, very, very low flow rate, just a trickle, well, at the very least, you have to add enough energy to overcome the delta Z. So if Q is essentially 0, you, as a minimum, have to add enough pump head to overcome the delta Z. But then if you want to have a higher flow rate than that, then you have to add even more pump head. So to solve systems, to find out what the actual operational flow rate is going to be, the operating point is where the pump curve and the system curve intersect. And so graphically, that's what it looks like for them to intersect. But you can set the two equations equal to each other, and you can solve for Q. That'll be the only unknown if you have HP equal to HP, where on one side of the equation is the system curve, on the other side of the equation is the pump curve. So here's the Jane equation, and what's the tricky thing about using the Jane equation if we're not yet sure? Let's go back just a step. We want to use the Jane equation so that we can find F in our frictional losses. If we don't know the flow rate yet, we can't know the F value because the F value depends on Reynolds number. And Reynolds number is a function of flow rate. So it's this endless loop of We're not sure what the flow rate is, but the flow rate depends on F value, but F value depends on flow rate, and so on. So what do we do in that case? What's that? It goes to 0, right, when we make what assumption? Right, fully turbulent flow, then this term goes to 0. We say we have a really high flow rate, so it means the Reynolds number is going to be big, and that second term. So begin by assuming fully turbulent flow. Okay, so let's work this example where we have a system with a pipe length that's 120 meters, and the water is flowing through a pipe diameter of 250 millimeters. We know the relative roughness of the pipe and some K values that's having to do with the bend and the entrance and exit losses, and then the water has to be lifted 9.1 meters. So we're going to use this information. This describes the system, and here is the given pump curve. This is what the pump can do. Now, just at first glance, we can know, is the pump going to be totally inadequate? And the first thing you want to look at is the delta Z, 9.1 meters. Is that delta Z bigger than the cutoff head? And no, it's not. So at the very least, we know the pump's going to be able to do something. The flow rate won't be 0. If the delta Z is bigger than that cutoff value, then the pump can't do anything. It wouldn't be able to lift the water high enough. But in this case, it can. So we'll proceed. The first thing we want to do is find the F value using the fully turbulent flow assumption. So 1.325 divided by the logarithm of 0.25 millimeters, 3.7 times 250 millimeters, and we square that. So just to begin with, as a starting point, we have 0.0196 as our F value. Okay, so we'll put that into the system curve equation. H sub P is 9.1. That's the delta Z that's described, plus Q squared. And now we'll do the friction term here. We've got an F value of 0.0196, a pipe length of 120 meters, 2G, so 2 times 9.81 meters per second squared. Now we need to put in the pipe's area. The pipe diameter is 250 millimeters. Area is pi d squared divided by 4. The pipe area is 0.04909 square meters. So that's where this 0.04909 meters squared comes from. And we need to square that, as it says in the equation, multiplied by d, 0.25 meters. Okay, so here's our friction term. We also need to have the local losses term. 2.4 is the K value divided by 2G times the area squared. So 0.04909 meters squared, square it. I'm going to write down some intermediate steps here just so I can double check my calculations. This is 198.98. Here is 50.76. And doing this is useful also just to look at the relative importance of the minor losses or local losses compared to the frictional losses. And it's about 4 to 1. The frictional losses are 4 times greater here than the local losses. So what we end up with is our system curve. Our system curve equation is H sub P is 9.1 plus 249.74 Q squared. Okay, so we have a system curve. It's the relationship between how much head is being added and what the flow rate through the pipe is going to be. Our problem-solving approach here is set the system curve equal to the pump curve. So let's do that. System curve equals pump curve. Okay, so 9.1 plus 249.74 q squared is equal to 24.4 minus 7.65 q squared. Okay, we'll combine the q's together. It's 257.39 q squared is equal to 15.3. Solve for q. Q equals 0.244 cubic meters per second. So that's the flow rate in the system. We could have solved this graphically as well. We could have just, using Excel, used a bunch of different Q and H sub P values to actually draw these two curves and find out where they intersect. And in fact, when I'm not trying to fit 2 lectures into one class period, I go ahead and start up Excel and demonstrate that. But this is really the quicker problem-solving method. So what should we do now? We found the flow rate, but very good. Yeah, you never want to assume that the fully turbulent flow is okay. So I did that. We want to check fully turbulent flow. Check fully turbulent flow assumption. It turns out that our velocity, Q divided by area, is going to be 4.97 meters per second, which gives us a Reynolds number, velocity times diameter divided by the kinematic viscosity, of 1.24 times 10 to the 6th. And the relative roughness, K sub S to D, is 0.001. If I look at the Moody diagram, the F value is unchanged. That puts us in the flat part of the Moody diagram. So F value is okay. We don't need to redo the whole thing with an updated F value. So really, I mean, this is all you have to do on a couple of those homework problems is interpret the description or interpret the drawing into a system curve and solve for HP. One of them actually, I think they give you the system curve, and then rather than the pump curve being this, you have to come up with the equation for the pump curve. I'll show you that in just a second. This is what those efficiency curves that you get from a manufacturer looks like. And this just looks like, I don't know, kind of like chicken scratch, right? All right. First of all, these different curves here are showing the same pump being operated at different rotational rates. And so if you're operating this same pump at 3,600 RPM, you could lift the water more than 450 feet compared to if you're only spinning at a third of that. If you're spinning it at 1,200 RPM, the water can only be lifted 50 feet as a maximum. And you'll notice that as the flow rate increases down here on the x-axis, as the Q goes up, then the head it's able to add decreases. The other thing I want to point out to you is that these curves here, they're kind of like contour lines describing the efficiency. And so if you happen to use this particular pump at these conditions right here, then it would be 65% efficient. Or, you know, at a lower flow rate, 64% efficient, and so on. But it looks like about the best this pump is going to do is 65% efficient. The last curves that are on here, NPSH, that means net positive suction head. And we'll get into that in just a minute, what the interpretation of that is. So before we move forward, did anybody want to ask Any questions about the example or this diagram of what the manufacturer's pump curve looks like? Okay, so this is maybe the trickiest of the homework problems that you're going to solve by Thursday. Yes?
Will we ever be asked to solve efficiency or anything like that?
I don't want to say no, never.
In this class?
In this class? You just gave me a really good idea for an exam problem. I don't think you are in the homework.
Okay.
But you mean like solve for it here?
Yeah, I just mean like, is there any way to actually like mathematically solve for it?
Sure, yeah.
There is?
Yeah. Yeah, you know, like if you were measuring the electrical consumption that's going into a pump house, and you know what the flow rate is, and you know what the unit weight of the liquid is, and you know the pressure increase of the pump, actually you could solve for the efficiency pretty easily. It wouldn't be too bad. Yeah. Thanks for the idea. All right. Okay, so on this homework problem, they don't give you an equation for the pump. They actually give you the figure. And so what you have to do is you have to turn this figure into a pump curve. So on this one, they give you the system curve, but you have to like digitize this figure to find out, you know, following this form, this is the typical form of the pump curve where we have some y-intercept. So the value where the curve intercepts the y-axis is this y-int. And then you have to have some c value that is such that whatever q's and h sub p's you pick out off of the curve, that c value makes it so that the curve best fits those points. So what that means is, you know, go through here and identify when the q is 0, what is the HP? When the q is 20, what is the HP? And so on. You know, you could do for HP of 100, what is the flow rate? 50, what is the flow rate? And so on. So that's like known from the figure. And then what you need to do is have some guess C value somewhere else, just like a cell at the top, a guess C value, and then use this equation to get a predicted H sub P using this equation based on the guess value of C. And then the difference between the known and the guess value of the H sub P's, and you want to minimize the average difference between the known and the guess value. So it's curve fitting. There isn't a way, you know how when you sometimes have data in there, you know, like if you have data like this, you can just tell Excel, hey, put a line in there and tell me the equation of the line. Unfortunately, Excel isn't going to be able to help you out this time, not in an automatic way. But what you can do is you can set up the spreadsheet like this and just play around with typing in constantly different C values until you see that you've got a small average difference between your known and your predicted H sub P based on this form of the equation. So that's the tip I wanted to give you on the homework. You may have to think about it a little bit more before this makes sense, but essentially you're taking this figure and you're turning it into numbers, digitizing it. I'll tell you a range. I'll tell you what the answer is between. What you should look for, it should be between 0.1 and 0.2. If you get it somewhere in there, the correct answer is between those two bounds. All right. For the C value. All right. You sure? All right. This is one that we're going to have to skip because we're cramming 2 lectures into one. Okay, cavitation is a risk when the pump is too high above the origin reservoir, or if you have a really long suction pipe, or if the suction pipe has too small of a diameter. Any of those 3 things is going to increase the risk that the water pressure gets really low before you get to the pump. So remember that what we said was the water pressure here is 0 since we're at the same elevation as the liquid. But then as we move through the pipe, the pressure is getting more and more negative. You know, as we go up, the pressure is becoming negative very quickly because we're changing elevation. But even as we move horizontally, the pressure is still decreasing because of pipe friction. And so anything that promotes a lot of pipe friction is going to cause this risk of the pressure getting really low. And remember, last semester in fluid mechanics, we talked about how there's two ways to boil water. You can either boil water by increasing the heat, and then it boils because the vapor pressure exceeds atmospheric pressure. The other way to boil water is not to heat it up, but it's actually to apply a vacuum, so that if the atmosphere that surrounds the liquid has a pressure lower than the vapor pressure, then little bubbles will form. And you may think, well, little bubbles aren't going to cause trouble. What's the issue? These tiny little bubbles, when they get onto the pressure side of the pump, collapse and send a shock wave through the water. And that one little bubble, the individual force of its shock wave may not be too damaging, but it's over the long term, millions and billions of these little bubbles collapsing and sending a shock wave towards the material that the pipe and the impeller that's made of can cause a lot of damage to the impeller. And so it's the pump actually gets pitted and the material will start to erode. In lab measurements, they've actually measured jet velocities when the bubble collapses and the water shoots inward towards the center of the bubble. The velocities can reach 110 meters per second and pressures of up to 800 megapascals. And so those are pressures about 100 times greater than anything we'd expect to see inside a pipe network. Here's an impeller that was damaged by cavitation. You can see that there's pitting on the outside edge of the blade. And this is where the pressure is going to be most negative, is on the outside edge of the blade. So avoiding cavitation can be ensured if you do these calculations that have to do with net positive suction head. And the way it works is you start with atmospheric pressure, P naught. And any one of these three things can get you closer and closer to danger. If you have a big elevation difference between the liquid and the pump, and so if we go back to this diagram, what would be more risky is if this pump was on a higher pedestal. So you can see right now it's pretty close to the liquid elevation. Here's the liquid, here's the pump. It looks like a pretty small Z value. But if you have the pump higher up, that's more of a risk. It's a higher problem. You can never have a pump more than 10 meters above the origin. That's on the suction side, because the maximum you see here, pressure divided by gamma. And so atmospheric pressure is 101,325 pascals. So 101,325 newtons per meter squared. And the unit weight of water is 9810 newtons per meter cubed. And so what that tells us is that at the maximum, even if there was no if there was no energy losses due to pipe friction, if all you are doing is a delta Z, about 10 meters is the most that you could lift the water on the suction side before you have a risk of cavitation. But it's not just suction. It is the head loss due to pipe friction and also the local losses, and then also the vapor pressure itself. And the warmer the water, the greater the risk is that it'll cavitate, because warm water has a higher vapor pressure. Vapor pressure is a function of temperature of the liquid. So warm water that's being lifted a high amount is at risk of cavitation. And so you look at the system and you find out how much NPSH is available. And then each pump has a manufacturer specified required NPSH, and that's just based on the flow rate. And if we went back to that efficiency chart, you'd notice that it had the NPSH required on there for different flow rates. And anytime the required is greater than the available, cavitation occurs. So I've taken the cavitation problem off your homework assignment just because we need to consolidate, but I still just wanted to expose you to the fundamentals of the principles and just let you know that cavitation occurs when you're either lifting water too high, if you've got a long suction length, or a small diameter pipe, any of those things can cause cavitation. And you may notice that actually when you buy a pump from a manufacturer, that oftentimes the suction size hose is a larger diameter than the discharge size hose. And that was the case when I was in graduate school. I had to buy a couple of pumps for an experiment that I was doing, and in each case they give you a really big fat suction size hose because the lower the velocity, you're going to have less losses due to pipe friction. And then the discharge hose was a smaller diameter because there's no risk of cavitation on the pressure side. It's just on the suction side that the cavitation occurs. So any questions about cavitation?
Yeah, that's when the pressure in the water is lower than the
Yeah.
atmospheric pressure?
Yeah, it's anytime the pressure in the water is less than the vapor pressure of the liquid. And I just can't resist. Let's go to this one, even though I said skip it. Remember, we can either boil the water by adding heat, or even at a low temperature, like 20 degrees Celsius at room temperature, if the pressure of the water goes below the vapor pressure of the liquid, like if the pressure of the atmosphere that surrounds the water, then it'll boil. And you remember the video where they were like pumping air out of that liquid, that like glass jar, and that's what made it boil. You can either have a low pressure by pumping out air, or you can have a low pressure in a system in this case just because energy is being lost due to pipe friction as you keep going along this. All of a sudden you may get to the critical point, and it may not be in the pipe itself. It might just be like right along the face of the blade that you've got that really low pressure. It might just be at one tiny little spot that the cavitation occurs, but that's enough. Any other questions? Yeah. Yeah. What you would need to do is you'd need to do this check to make sure that the available NPSH, you want the available NPSH to be bigger than what's required. You want to give the pump the suction head that it requires to prevent cavitation. And usually it's not an issue. You know, you'll be able to put the pump somewhere close to the origin reservoir, or if you want to make sure that it is below the liquid surface. So you remember, like when in this typical example, when we say we're pumping from here up to here, well, this pump is below the liquid level, and so it's not going to cavitate because, you know, maybe the pressure is going to decrease a little bit, but as long as the pump is below the liquid level, then we're fine. The issue would be if we have the pump actually physically situated here, and we've got a pipe going down there. Now we need to be a little more careful because this delta Z might be too much already. That might be causing too much negative pressure inside the suction side line.
Just use maybe like some smoother pipes.
It would help. Yeah, it would help. But even if this is totally smooth and there's no friction losses, there's a point where the delta Z alone is too much to overcome what we're working with. And what we're working with is P naught divided by the unit weight. So if the delta Z is bigger than this first term, then you're out of luck. All right. So I would like you to take a crack at this example. We have a system that's described, the F values given, so you're not going to have to use the Jane equation, you're not going to have to do fully turbulent flow. Let's just assume we know F, and there's losses due to pipe friction here, but we also are going to have some local losses. We're going to have let's have a local loss of an entrance loss of 1, and there's also going to be velocity head as it's being discharged into the atmosphere. So you're going to have to work into the system equation the fact that the velocity head is still there. Now you have a problem that's similar to this, and it's asking how long does it take to pump a certain amount of water. So basically set system curve equal to the pump curve and solve for Q, and then once you know the flow rate, then you can calculate the time. So I'm going to give you some time to get a head start on this. I'll circulate around and see that you're going in the right direction, and then we'll work through the rest of it together. As you already know, we're trying to cram in too much stuff into one day, so what I'm going to do is I'm actually going to email you a pen cast of this example. I don't think we've got enough time to do this and also talk about the pump scaling laws that we need to also cover for the homework. So let's just pause this example. I'll email you a pencast PDF within a couple of minutes of class being done, and we'll turn our attention to these affinity laws. And what affinity laws are used for is to describe the situation when a pump is being operated at different conditions than it was originally intended for. Or maybe there could be a pump that has the same shape and the same basic operational parameters, but it's a different diameter. And so here's an example of, a certain manufacturer makes a pump in both a 2-inch diameter and a 3-inch diameter. That's the diameter of the discharge hose that would come out of a pump. So there's a series of relationships. It's similar to dimensional analysis. If you remember Chapter 8 from fluid mechanics, when we were trying to describe what the performance of a prototype, how a prototype's performance can describe the relationship between a prototype and a model. And in these scaling laws, it allows you to find out how a pump is going to behave if you change the rotational speed, if you have a different diameter of the impeller, or if it's a different flow rate is desired. And so just to illustrate how these affinity laws work, we'll work through a couple of examples here. And then I think with this last example in the pencast I sent you, you'll be able to do the assignment that's going to be due on Thursday. So let's say that we have some pump that normally operates at 1200 RPM and it has an impeller diameter of 8 inches. That pump is given a curve. The manufacturer gives a pump curve of 12 minus 0.1 Q squared. So if you use something called a variable frequency drive, that's a way of changing how a pump operates. A variable frequency drive, it changes the electricity that comes out of a wall. Like, right now it's alternating current at 60 hertz, which means it goes back and forth between positive and negative 60 times in a second. A VFD changes the frequency of electricity, and that's how you can get a pump to operate at a different speed than it normally is set for. So let's say we use a VFD to change it to 2400 RPMs instead of the original 1200 RPM. So what we want to do in a problem like this is find out what will the performance curve look like if we have a different rotational speed. So the original pump curve is H sub P is 12 minus 0.1 times Q squared. And this is at N is 1200 RPM, and the diameter is 8 inches. Okay, so what we want to do is we want to change the N value to 2400. So the original N1 is 1200. We want N2 to be 2400 RPM. We're going to leave the diameter of the pump the same, just spin it twice as fast. So of those equations that were on the previous slide, what applies to us is the relationship that Q1 divided by N1 is equal to Q2 divided by N2. And then the other thing that applies is H sub P1 divided by N1 squared is equal to H sub P2 divided by N2 squared. Those are the two relationships. And here, since the diameters are the same, I didn't include diameter in these formulas over here. I've just D1 equals D2, so those drop out. So what we're going to have to do is substitute in what we know once we've rearranged this equation. So Q1 is N1 divided by times Q2 divided by N2. So that is 1200 times Q2 divided by 2400. And so what that tells us, the relationship between Q1 and Q2. Q1 is 0.5 Q2. And then we also rearrange this equation to give us H sub P1 is equal to 1200 squared divided by 2400 squared times H sub P sub 2. So that is 0.25 H sub P2. So we know the relationship between Q1 and Q2 and H sub P1 and H sub P2. And we put that into the original expression for the pump curve that was given by the manufacturer. So the manufacturer said that the pump curve is that has a cutoff head of 12 meters. That's the maximum it can lift. And then as the flow rate increases, the pump head decreases. So originally it was H sub P1 is equal to 12 minus 0.1 Q1 squared. This is the original pump curve. We substitute in those values that we just solved for. So 0.25 H sub P2 is put in place of H sub P1 equals 12 minus 0.1 and 0.5 Q2 squared. So what that gives us is HP2 is 48 minus 0.1 Q2 squared. So this is pump curve at 2400 RPM. So by spinning the pump twice as fast, we've quadrupled the cutoff head for this. All right. So that's if it's 2400 RPM. We do a similar thing if we are going to keep it at 1200 RPM, but we want to switch to a 10-inch impeller. So now we'll just say we want to have, for the diameter 1 originally was 8-inch, and we want diameter 2 to be 10-inch, but everything else stays the same in this second bullet point here. So what is the pump curve going to look like? Okay, so in this case, we have to look at these, and we're having it still be the same rotational rate, so N1 equals N2. So what we're going to be substituting is Q1 divided by D1 cubed is equal to Q2 divided by D2 cubed. And then the other equation is going to be H sub P1 divided by D1 squared is equal to HP2 divided by D2 squared. So the rotational rates are the same. We don't need to bother writing them in. Okay, we can rearrange this one. It becomes Q1 is 8 inches cubed times Q2 divided by 10 inches cubed. Okay, so Q1 is 0.512 Q2. And here this transitions into HP1 is 8 inches squared divided by 10 inches squared times H sub P2. So that is 0.64 H sub P2. So now we have a relationship between HP1 and HP2, Q1 and Q2. We put it into the original. So the original equation was HP1 is 12 minus 0.1 Q squared. We just make the substitution. So 0.64 H sub P2 is equal to 12 minus 0.1, make the substitution, 0.512 Q square, Q sub 2. We need to square it. So in this case, HP2 is 18.75 minus 0.04096 Q2 squared. So if someone asked, what's better? Is it better to keep the 8-inch and spin it twice as fast? Or is it better to increase the impeller diameter from 8 inches to 10 inches? You can look at this new pump curve and see that spinning it faster gives you a greater increase in the lifting capacity of the pump. If you have a bigger pump, bigger diameter, rather than spinning it faster, you're not going to increase the lifting capacity nearly as much. Okay, we're out of time, so I'm not going to be able to, oh, well, if you need a pump to lift it 30 feet, the one that's best is this one. You know, this one wouldn't pump the water 30 feet because it can only pump the water at most 18.75. All right, so that's it from today. I'll send you that example that we weren't able to finish. Just to take one last look at these announcements, remember that we have an exam on Thursday. You can prepare an equation sheet that's one page, front side only, and it'll be fun. We'll take 60 minutes for the exam, then we'll introduce the design project.
Should we bring our personal computers?
No. All right, I'll see you on Thursday.